Okay, welcome back to step 2. And I'm going to walk you through is really what do we do once we decide that we can assume a product solution. So as you looked in the reading, some of you might be confused or wondering why we can say that u of xt can be written as a function of x and a function, the product of a function of x and a function of time. And the really dissatisfying answer is because we have done extensive research and have shown that this is, in some cases, at least in this one for sure, a valid assumption. Again, this was all in the reading, but I wanted to sort of reiterate that this is due to the fact that we know so much about these differential equations, these partial differential equations, that we can a priori decide or assume a product solution. So what I would like you to do in your work is, no kidding, to say, assume either u of xt is equal to x of x and t times t of t, or assume product solution. And what this product solution allows us to do is it actually does allow us to use the method of separation of variables. So it really justifies, assuming this product solution justifies our use of this method. So it's important to me that you write this down, just so you know that you are really truly making an assumption. Turns out the assumption is going to work, but you really are making an assumption. Okay, so now what do we do once we have made this assumption? Well, it is actually no different than in ODEs. In ODEs, if we had a linear ODE, we assumed a trial solution y equals e to the RT. And then what you do is you take the appropriate number of derivatives and you just stuff that back into the ODE. So we're going to do exactly the same thing. And you're going to see actually just how helpful it is to break up this unknown function u of xt into a product of two functions. One only depends on x and the other one only depends on time. Okay. So the first thing we notice is that we have a first derivative in time and we have a second derivative in x. So let's do the first derivative in time. So du dt is going to be equal to, okay, so now in this particular case, we can hold x constant. So x of x doesn't change, it's just x is a constant, this is a partial derivative. And then t, we just have the first derivative of time, okay, the t function. Similarly, del squared u del x squared. Well, now this time we can hold the time function constant, and now we have a second derivative, and this is a straight derivative, right? So this is a full derivative, x double prime of x. So now we substitute back into our PDE. And what does this give us? So this gives us the x of x t prime of t equals k. So don't forget about the k. It'll be really easy to do that. Times t of t x double prime of x. Okay? And now we do exactly what the method says. We separate the variables. So what I want to do, separate the variables. I want to get all of the x functions on one side and all the t functions on the other. So what I'm going to do is and then k really could go anywhere. It has to go somewhere, and it could go with either the time functions or it could go with x functions. So conventionally, it goes with the time function. So that's where I'm going to take it. So on the left-hand side, I'm going to let time stay over there. So t prime of t divided by, and I'm just going to divide by the t of t on the right-hand side and k. So k, t, t. And that is equal then to x double prime of x divided by x of x. Okay, so this is where I'm going to stop. Now I want you to go to step 3 and read through the entire several paragraphs about the separation constant. And just to prep the battlefield here, this is a potentially challenging concept at first, but I encourage you to read through slowly and then convince yourself this is true. And once you've done that, then I think the rest of this is going to go very, very smoothly. So there's just one interesting, clever trick. And then once you get that, the rest of this process is just a little bit of grungy math. So I will meet you back here for the next video.